This tutorial is about solving ordinary differential equations using numerical methods, and in particular we'll talk about second order differential equations. Um, so in that case, we usually have a second order derivative which provides us the a function of the independent variable, the dependent variable, and the derivative of the dependent variable, possibly the first derivative, and some initial conditions. So we know the value of the function at the initial point, and we also know the value of the derivative of the function at that initial point, and that's why these kind of problems are also called initial value problems. And what we can do is we can convert this second order derivative into two first order derivatives by defining a function of the derivative of the function itself. So that way this can be converted into a vector equation. So let's define y vector, which is y0 and y1 stacked, and this gives us instead of having a second order differential equation in a scalar quantity, now we have a first order differential equation in a vector quantity. And that's kind of the trick we play. And then once we have the first order differential equation, we can apply Euler's method the way we have already developed it before, and solve for the vector itself. And as we are solving for this vector, we are not only getting the function that we are interested in initially, but we are also getting the derivative of the function from this method. So to demonstrate this, let's look at the problem of free falling, and this is also called explicit method because the new value of the y function depends upon the old value, so we can basically just keep moving forward at each time step or spatial step. So this is the same problem that we did in the previous lab. The only difference is that there we dealt only with the dv by dt is equal to mg, but now we're going to take into consideration the position. At that point we took care of the position by just adding another line in the code, which was potentially dy by dt is equal to v, and we solve this. But in this case we're going to actually create two differential equations that are first order differential equations. And so now we have the position, the rate of change of position is velocity, and rate of change of velocity is the force itself. And so when we vectorize it, we define a S vector, which potentially is another is a symbol for the state vector. So that the state of the object has its position and velocity, and a function which is the slope of the function that we are interested in. And so that is the right hand side of this set, and the initial conditions are the information that is given to us, that initially it's at 50 meters height, moving down or moving up with the velocity of 5 meters per second, so that becomes S0. So with these informations available, you can think of this as two equations in the form of matrices. So this top equation is same as we did in our previous implementation. The y at n is the previous y plus velocity times dt. That's this first part. And then the second part is velocity at the next step is the previous velocity plus mg times dt, which is right here. So instead of using it separately, we solve it as a vector equation. So a quick implementation is just changing this code to handle that. So I have done that here, and instead of having the initial condition as two separate variables that we had before, y0 and v0, we create a new variable s0, which has both the initial conditions. And x, we still need x because we need to plot it. And then in a similar manner, we want to run it up to 6 seconds with the increment of 0.1 seconds. So that gives us our time domain and time stepping that we want to do. And then let's define s variable that we are interested in. And the first value is the value of s at time 0, or the initial condition. And note how this is now n by 2. So it's at every time step we are going to be getting the position value in the first element and velocity value in the second element of this array. And we define it the same way we did it before. And then in the loop we have the position or the state vector new value is equal to the state vector's old value plus the function itself, which is the previous velocity and mg. So this is the previous velocity and mg. So vi appears here. So previous s value's second element, which is here, is also appearing here as the first element. And then the second element of this function is mg, which we know here, mg, this one or this one, times dt. And this is our update portion of the function. And now we want to plot it. So now we have the position and the height, or the position in the s vector. So we can do that. Of course, the value of x, actually we don't even need to put there, it can be 0. So s, the first value of the element s at this time is the position, and we want to put the second value as the vector. So that basically completes the code. Now if we run this code, it should give us exactly the same functionality as before, but the advantage is that now we are using vector instead of individual scalar quantities. And you will see how switching the model to vector is going to make this code much more adaptable to to higher order differential equations. So this concludes this tutorial.